Hello everyone. In this video, I talk about higher order derivatives. Since we know that the derivative of a function is itself a function, so it means we may take its derivative. Thus, a higher order derivative refers to repeating the process of differentiation. This becomes more relevant to curve sketching or maxima and minima problems or motion problems, and there are some other applications which we're going to discuss in future. So first we know that we start with a function and then we take the first derivative of the function. So this is called first derivative. And if we take the derivative again, so take the derivative of the first derivative, so that would be called second derivative. And similarly, if you take, so this can also be written as d2y over dx squared. So that is the notation for second derivative. And next, if you take the derivative of the second derivative, then we get third derivative. And again, the notation is d3y dx cube and so on. So these are our higher order derivatives. And here I have written the different notations in fx form, f prime x, f double prime x. So we put 2 dash and 3 dashes on the top. Similarly, y, y prime, y double prime, y triple prime, and so on. Or the one we discussed just now, y dy over dx, d2y over dx square, and so on. Let's do this example problem and find the first, second, and third derivative of this given function. So we are given y is equal to 6x squared plus cube root of x plus 9. So I'm just going to rewrite this function. So y is equal to 6x squared plus x raised to power 1 over 3 plus 9. So first we're going to take the first derivative. And when we take the first derivative, we know that derivative of x squared is 2x. For x raised to power 1 over 3, we can apply power rule. So bring the power down, reduce the power by 1. So 1/3 minus 1, so that would be negative 2 over 3. And derivative of 9 is 0. So thus we got our first derivative 12x plus 1 over 3 x raised to power negative 2 over 3. So that is our first derivative. If you want to take the second derivative, so now we're going to take the derivative of this expression. So second derivative would be, so take the derivative of 12x, which would be only 12, and then derivative of 1/3 x raised to power negative 2 over 3. Again, bring the power down, reduce the power by 1. So negative 2 over 3, negative 1. So that will give us common denominator is 3. So negative 2, negative 3. So negative 5 over 3. So we get x raised to power negative 5 over 3 at 12 minus 2 over 9 x raised to power negative 5 over 3. So next we're going to find our third derivative. So we're going to take the derivative of this expression again. So we get third derivative would be, so derivative of 12 is 0. So minus 2 over 9 is just a constant factor. And bring the power down, reduce the power by 1. So in this case, the power will be negative 8 over 3. So overall, we get third derivative is equal to 10 over 27 and x raised to power negative 8 over 3, or if you want you can write this as positive exponent, or you can even write this as 10 over 27, so x raised to power 8 cube root of that. So any form is fine. So this is our third derivative. So therefore, for the higher order derivatives, we just keep on repeating the process of differentiation. Let's take a look at another example in which we have to find the 21st derivative of this function. Wow, that sounds weird, right? 21st. So it means you have to take the derivative 21 times? Maybe not. Let's see if we can see a pattern in the derivatives. So we start by taking the first derivative of this function. So first derivative would be, so derivative of x raised to power 20. So bring the power down, reduce the power by 1, and then negative. So bring the power down, reduce the power by 1. Again, bring the power down, reduce the power by 1 minus 0. So that's our first derivative. Similarly, if you want the second derivative, so we already have for 50 times 20 times 5, which is 100, x raised to power 19. So bring the power down, reduce the power by 1, and we got an x18 term. And similarly, we're gonna get, so 13 times 7, whatever it is, 6x5, and then, so 2 times 3 is 6, and then x square, derivative of that would be 2x, and so on. So you will notice that. So now I'm not going to do the whole steps. I'm just going to show you what, like, how we can extend our thinking. So if I take the third derivative, so I'm going to get a term, leading term, where I'm going to get 17 power, and here would be some coefficient. So some coefficient times x raised to power 17, and maybe a few more terms. Similarly, if I take the fourth derivative, I would get x raised to power 16, right? And so on. So let's write it by 4. So if we notice, so when we had first derivative, the highest power was 19. So 19 plus 1 is 20. Then second derivative, the highest power is 18. 18 plus 2 is 20. Third derivative, highest power is 17, and so on. So if we have the 20th derivative, so in this case, y raised to power 20. So y, so 20th derivative, then we're gonna get some coefficient, and we're gonna get x raised to power, the sum should be 20, right? So x raised to power 0, and x raised to power 0 is just 1. So it means in the end you're gonna have a constant term. And when you take the 21st derivative, so which is y 21st, so that would be 0, because you are taking the derivative of a constant. So thus, just by noticing the pattern, we can find the 21st derivative of y. So that would be 0. One of the applications of higher order derivative is that we use those in the motion problems. So if we start with the distance function s, which is dependent on time t, so let's say s is our distance function and t is our time. So let's say we use notation v for velocity and a for acceleration. Since velocity is change in distance over time, so if you take the derivative of distance function with respect to time, you get your velocity. So change in distance over time, ds over dt. So in this case, if you want to find the velocity, so that would be the derivative of our s function, distance function. So t square plus 5 raised to power 4. And in this case, we have inside function t square plus 5, we have outside function, which is our power function. We're going to apply the chain rule, because here the variable is t, but here we have some other expression in place of t, so we apply chain rule. So what we do, so first, so something raised to power 4, bring the power down, reduce the power by 1, and then take the derivative of inside. So in this case, we get 4t square plus 5 cube, and then derivative of t square plus 5. So it will be 2t plus 0. So only 2t. So overall, we get 8t t square plus 5 whole thing raised to power 3. So this is our velocity function. And next, if we want to find the acceleration, so acceleration is change in velocity over time, so which is dv over dt. And since we already know that v is equal to ds over dt, so that's how we get acceleration is double derivative of distance function. So that gives us acceleration. So in order to find the derivative of velocity, that will give us acceleration. So in this case, we can use the product rule. So we have u times v. So where u is equal to 8t and v is equal to t square plus 5 whole cube. So our product first function as it is, derivative of second 1d2 plus second function as it is, derivative of first. So again, so when we take the derivative of t square plus 5 whole cube, so first bring the power down, reduce the power by 1, and then by chain rule you need to take the derivative of inside, which will be 2t. Similarly, again for derivative of 8t we get 8. So let's do some algebraic simplification. So take any common factors out. So 8 is out, t square plus 5. So 2 powers can come out. So inside we are left with 6t square. And here we are left with one copy of t square plus 5. So overall we get 8t square plus 5 square, and here we get 7t square plus 5. So this is our acceleration function. Thus, if you are given the distance function, you can find the velocity and acceleration. So velocity is the first derivative of distance function. Acceleration is the second derivative of distance function. So since now we know how to find velocity and acceleration, so let's take a look at this example. So take a moment to pause this video and read the example first. Say a particle is moving with a distance function, this one 1.1 t square minus 5t. We need to find velocity after 10 seconds. So since this is our distance function, velocity is first derivative of distance function. So that is our velocity. So that would be uh, derivative of t square would be negative 5 would t would be negative 5. So we get 2.2 t minus 5. But we are interested. So this is our velocity at any time t. We are interested in finding velocity when time is 10 seconds. So just put t equals to 10 in this function. So we get 2.2 times 10 minus 5, which is 22 minus 5, 17 feet per second. So on the top we have the units of distance, which is feet. On in the denominator we have time, which is seconds. So that's why we get feet per second. Next, we're going to find the acceleration of the particle. So acceleration is second derivative of the second derivative of the distance function, or first derivative of the velocity function. And we can write different notations for acceleration, or you can write even v dash t. So in this case, we're going to take the derivative of our velocity function, which is 2.2 t minus 5. So acceleration is 2.2, and the units will be feet per second square. So in this case, we notice that we have the constant acceleration. So next we're going to find when is particle at rest, or the object at rest. So object would be at rest when our velocity is 0. So for that we solve vt equal to 0. So this implies our vt function is 2.2 t minus 5 equals to 0. So we solve for t. So 2.2 t is equal to 5, or t is equal to 5 divided by 2.2, which in turn means t equals to 2.3 seconds. So particle is at rest when after 2.3 seconds. Let's do another motion problem for practice. Take a moment and read this problem, and even you can try this problem on your own. So a bullet is fired in upward direction and its height after t seconds is given by this function. So basically we are given the distance function. We need to find the initial velocity of the bullet. So we start by finding the velocity of the bullet, which is the first derivative of distance function. So in this case, if you take the derivative of 600t, so it will be 600 minus 5 times derivative of t square, which is 2t. And we get 600 minus 10t. But our goal is to find initial velocity. It means when the time is 0. So when t equal to 0, initial velocity would be, so you simply plug in t equal to 0. So V0 would be 600 minus 10 times 0, so which is 600, and velocity is meter per seconds, because height is given in meters and time is given in seconds. So next we're going to find velocity at t equals to 2 seconds. So it means we just put t equals to 2 in this function. So we got 600 minus 10t. In place of t we put 2. So we get 600 minus 10, which minus 20, which means 580 meter per second. So that is velocity after 2 seconds. Next we're going to find the greatest height of the bullet. So if we think about this, so this is a quadratic facing downward, so it's like a parabolic equation, parabolic trajectory. And when we say that the greatest height, so we know that at the greatest point, so if you draw the tangent, what's going to be the slope? So slope is going to be 0. And this is your distance function, so this is your s. So slope of this function is 0 at the highest point. So that means the velocity is 0. So at that point, you're going to attain the greatest height. So for this one, what we do, so greatest height means, slope is 0. So we plug in our velocity function. So this was our velocity function, equals to 0, and solve for t to find the time. So time when it attains the greatest height. So it gives us that t is 600 over 10, so which is 60 seconds. So it attains the greatest height at 60 seconds. And since our goal is to find the height, and for height, you can simply use 60 in your s function. That will give you height at 60 seconds. Therefore, greatest height, it means s at 60 is equal to, so 600t, 600 times 60 minus 5t square, 560 square, and when we solve it we get 18,000 meters. So that is the greatest height attained by bullet. Lastly, we're going to find the acceleration of the bullet. So in this case, acceleration is just the second derivative of the distance function or the first derivative of our velocity function. So derivative of velocity means derivative of 600 minus 10t, and derivative of 600 is 0, derivative of negative 10t is negative 10. So acceleration is negative 10 meter per second square. And since acceleration is constant and it has negative value, So negative value means it's decreasing. The speed is, the velocity is decreasing. So I hope this makes sense. Thanks for watching this video.